Our first speaker today is Zhiqiang who's going to talk from Peking University, who's going to talk about rigidity and quasisymmetric uniformization of combinatorial Thurston maps.
Okay, thank you. And I want to thank the organizers for inviting me, giving me this opportunity to speak at the field. Actually, time flies, and I've spent many days and nights, about 20 years ago, started attending seminars, talks, study mathematics as an undergraduate student here, and finally I get this honor to speak here. I really appreciate that. And as the title suggests, it's going to be about Thurston maps, actually more precisely, expanding ones. So this is a work that I joined with Peking and a very brilliant student of mine, who is a first-year PhD student now, Han Yunzhen, to generalize the great theory of Bank and Meyer to higher dimensions. So as a result, I think the talk really was, partly was going to be attributed to Daniel, who would have been in the audience, but unfortunately, as some of us heard, that he has some emergency and had to do a last-minute surgery last night, and but everything was, I heard, fine. So I really appreciate all the things I learned over the years from Daniel, and hopefully he'll have have a chance to listen to my talk later. And then lastly, I think this is also my first response to Misha Lubitch, to his remark, first sentence to me as a postdoc in Stony Brook, that the future is in high dimensions. Okay, so the talk is going to be meant to be a kind of introductory and non-technical one, and I apologize if I ever cannot help to go into details, but this is the plan. We want to discuss a generalization of Thurston maps on higher dimensional manifolds, which we call a combinatorial Thurston maps. And in these maps, in particular, we want to prove that they admit cellular structures as Thurston maps, even though in two dimensions, the cellular structure is relatively easy to obtain. In higher dimensions, it's much more technical. And also, you need to get the right definitions. And then once we impose the expansion condition, as in the work of Bank and Meyer and Zhiqiang Pilgrim, we can obtain we can construct a visual matrix for which we prove quasisymmetric uniformization theorem. And we can, while doing it, we also establish some rigidity result for uniform quasi-regular maps. Okay, so let me recall you the notion of Thurston maps in two dimensions on two spheres. So, in particular, it is a branch cover. So what do we mean by branch cover? In two dimensions, it's pretty concrete. It basically says that locally, it looks like z to the power d. So, but more precisely, each point, there is a neighborhood around it and a neighborhood around its image, and two separate orientation preserving homeomorphism, two separate charts, phi and psi, through which the map look like z to the power d. Okay, that's the behavior of branch cover in two dimensions, very concrete. And and we call the number d the local degree of the map at this point. And then when the local degree is strictly bigger than 1, we call the point x a branch point or a critical point for the map. And the post-branch set or the post-critical set is defined to be the union of forward orbits of, strict forward orbits of the branch points or critical points. And what is a Thurston map? A Thurston map is nothing but a non-homeomorphic post-critically finite branch cover. By post-critically finite, I mean the post-critical set is a finite set. Okay, so that's in two dimensions. Okay, so let me give you a slight non-trivial example, but very popular one. A pillow with a flap. So we have two copies of square and then paste them along the boundary, then we get a pillow. But on the pillow, we we attach an open envelope. We cut it open and attach an open envelope along the wand and get a pillow with a flap. And each little square is mapped to one of the two sides of the pillow, and we can identify the image by with the domain by like smash down the envelope to make it part of the front square. Okay, so this way we get a simple example, a simple but non-trivial example of Thurston map. Okay, so first result, first property of Thurston map that is very important is, well, it admits a sequence of so-called cellular decompositions. Okay, so in particular, Bunker-Mayer proved that there exists a sequence of cell decompositions of S2. Once you give, derive from any given Jordan curve, as long as the curve passed through the finite many post-critical points. So very there are many such curves, but any such curve admit a sequence of cell decompositions. What exactly do we mean by cell decomposition? A cell decomposition is a locally finite cover of in more general setting, a locally compact Hausdorff space by cells. What do you mean by cells? Cells are subsets that are homeomorphic to a Euclidean ball of some dimension. And such a cover need to satisfy two conditions. For distinct cells, their cellular interior. So that corresponds to the cellular interior corresponds to the boundary of the Euclidean ball through the homeomorphism. Interior of the Euclidean ball through the cellular through the homeomorphism. Okay, should be disjoint for distinct cells, and the cellular boundary, which corresponds to the boundary of the Euclidean ball through the homeomorphism, through the identification, is a union of other cells in the decomposition. This kind of cover is a cellular decomposition, just like the one we saw in the previous picture. Okay, and a map is cellular. A map F is cellular, or more specifically, D prime decellular for two different cellular decompositions. If you restrict the F, the map, to any cell, you get a homeomorphism. Okay, and cellular sequence means if you have a sequence of cell decompositions, and then the map has to be cellular with respect to any consecutive pairs in the sequence of decompositions. Then we call the sequence a cellular sequence of the map. Okay, yes.
Why can't you take this any cellular decomposition to get reimage and pull it
Yeah, that's how you construct. So the relation to C is exactly what you said. How you construct the cellular decomposition. You pull back C. So as long as the Jordan curve goes through the post-critical points, you can pull back C, and you get nice cellular decompositions. Okay, and in particular, those ones, the post-critical points are always vertices of the cellular decomposition. Yes. Not yet, and not in general. Not in general. So in this talk, usually it's not. Okay, so if it's Markov, as you suggest, then things would become even more easy to control, more understandable. But this is a general setting. That's what. Well, I mean, yes. I don't like the word trivial in math, but yes. Yes, in 2 dimensions. Okay, but what about higher dimensions? That is much more complicated. All right, so as we saw in the previous example, now we don't bother, making the 2 copies of the square, like distinguishable, so that we can iterate and still have pictures that are recognizable. You pull back this cell decomposition, you get this one. You have to imagine that you push down, you crush down everything to the same sphere. But combinatorially, this is the first iteration, this second iteration, this is the third iteration. Okay, and becomes very fractal and complicated quickly. All right, I think probably should speed up. So now, what about in high dimensions? So what we call combinatorial Thurston map is in the setting of branch cover on oriented closed connected Riemannian manifolds of dimension n. And but in this setting, a branch cover is just a discrete open continuous map. Okay, and under what condition does such a map admit a cellular sequence as in the case of Thurston maps on 2-sphere? Okay, so the issues, for example, the notion of post-critically finite condition fails for all dimensions bigger or equal to 3, because the branch set for such a branch cover, as long as it's not empty, it is of the branch set, its image, and its preimage. First of all, a branch set does not contain isolated points. And more concretely, by Chernovsky-Vassala theorem, the branch set, its image, and the preimages are all of codimension at least 2. So these sets are much more complicated than the post-critically finite branch set, the branch set for the post-critical finite maps. And so we need to generalize the post-critical finiteness condition by making topological combinatorial assumptions on the branch set and the post-branch set. That's the idea of us to design the definition. So here comes the definition of our combinatorially post-critical finite condition. So well, a map satisfies the combinatorially post-critical finite condition, or is a CPCF map. C, the first C is combinatorial, and then PCF, so CPCF map. If there exists a cellular sequence of the post-critical set PF, having the following 3 properties. Okay, so the first property is the original cell decomposition of the post-critical set P admit a refinement cell decomposition P0, such that the map restricted to the post-critical set is cellular with respect to the pair. Okay, and then secondly, what about the branch set, the preimage points of the post-critical set? Well, there exists a branch cover. There exists a cell decomposition of the branch set, such that with respect to the branch set and with respect to the cell decomposition on the branch set and the cell decomposition on the post-branch set, the map is cellular. Okay, and in particular, cellular in a nice way, in a way that the multiplicity of the map is constant in the interior of each cell. In the interior of each cell, the branching is very tame, is very, yes.
Sorry to interrupt. Just curious, could you do an equivalent definition, just asking that the map be piecewise linear and then the orbit, the branch and faces are finite?
There is some piecewise linear version, yes. Yes, but that's not what we consider, because we want to consider more general maps. Yes. Okay. So, and actually we were debating whether we want to write another paper on the piecewise linear class maps, but anyway. Okay. And then thirdly, the cellular decomposition on the post-critical points, the post-branch points, should be included in a cell decomposition of the whole space. any cell decomposition, as long as it included this the cell decomposition of the post branch set or as a subset, that's fine. That's good enough. Okay. We in particular don't impose a Markov condition on the cell decomposition of the whole space. Okay, and then well, here is the local multiplicity. Yeah, I mean, it's complicated formula, but it's like understood in the usual way, naive way. And then we call all the four cell decompositions the CPCF data of F. All right, so it's a bit technical, but so we can put the things into a diagram. So we have a cell decomposition of the branch set, and it map cellularly to the cell decomposition of the post-critical post-branch set, and then it has a refinement P0 for the pair. The map is cellular, and then the cell decomposition of the post-branch set is embedded in a cell decomposition of the whole space. Okay, and then if a map oriented closed oriented topological n-manifold is CPCF, but not homeomorphic of topological degree at least 2, then we call it a combinatorial Thurston map. Okay, and in particular in dimension 2, it's a Thurston map.
Yeah. Sorry to interrupt again. So when you're saying that it's a combinatorial Thurston map, it means that in this case the combinatorial data determines the map?
Not necessarily. I mean, up to it's a it's the deformation. Yes, yeah. So it is as written a continuous map on a topological n-manifold. No, we don't modular some equivalence relation at all at this point. Okay, so now what does the combinatorial data give us? The combinatorial data give us well, 3 sequences of cell decompositions of the 3 sets: the branch set, the post-branch set, and the whole space. And so with respect to which each consecutive pairs are cellular. Okay, so this is a technical result that is, as some people observe in dimension 2, it's just pulling back the Jordan curve. That's very simple, but as Tanya said, but in higher dimensions, you really have to do the work. Okay, but this is well, skip the technical part and then move on to the notion of expansion. Okay, so the notion of expansion is similar to that of Bunker-Mayer and Heisenberg-Pilgrim. You can either use the cell decomposition and its pullbacks, or use some open cover. So the first idea is Bunker-Mayer. The idea of open cover is from Heisenberg-Pilgrim. So you pull back, the cell decomposition as long as the mesh or the maximum diameter in the mth cell decomposition, as m go to 0 or go to infinity, decrease to 0, then we call the map expanding. And the notion of expansion, as in dimension 2, is a topological notion. It does not rely on the choice of the sequence, as long as the sequence make the map a CPCF map. And it does not depend on the metric as either, so which is not written on the slide. Okay. All right. Then once you have expanding combinatorial Thurston map, then it's a topological notion. So you want to define out of the topological map nice metrics using Sullivan's dictionary, which was mentioned in this talk already, in this conference already, and in particular by Sabia, among other people. And the notion of visual metric is a bread and butter for geometric group theorists. But the notion of visual metric in dynamics was introduced by Bunker-Mayer and Heisenberg-Pilgrim. So we can do similar things to construct the visual metrics for us. So we can use in particular the separation level. So a separation level for a cellular sequence between 2 points is defined to be the the biggest level, the biggest sub-index or in the sequence in which there exist two cells of highest dimension containing both either points respectively, and so that the two top dimensional cells are non-disjoint. Okay, and this notion plays a similar role to Gromov product. Okay, so using the picture previously, well, this is a different map, but you know, you can see if you have a sequence of cell decompositions and 2 points x and y, then well, in the first level, in the second decomposition, D2 doesn't work. D3 actually works. There is a two cell that contain both either points and then have non-trivial intersection. But or another level, D4 doesn't have such two pair of cells. So 3 is the number for the separation level of the 2 points with respect to the cell decomposition. Okay, then we can define the visual metric using the separation level. So a metric on the Riemann sphere, Riemannian manifold cell on the a metric on the Riemannian manifold is a visual metric for the map if there exists a cellular sequence such that with respect to this cellular sequence, the metric, the distance is comparable to some lambda to the power the separation level. Okay, and this quantity lambda bigger than 1 is called expansion factor of with respect to the visual metric. And a similar construction was done by Bonk and Meyer using cellular sequence, and Heisenberg and Pilgrim using using open covers. Even though their visual metrics are not by Lipschitz equivalent, they're quasi-symmetrically equivalent, but not by Lipschitz equivalent. Okay. Well, visual metrics exist and induce this, you know, have all the nice properties, induce the given topology on the manifold and well-defined, etc. All right, now, probably I should mention that visual metrics turned out to be very useful in study dynamics of non-uniformly expanding dynamical system as in the case of dimension 2. So many of my works in ergodic theory and dynamics for such maps in dimension 2 uses crucially visual metrics, such as prime object counting, such as ergodic optimization. So these metrics are not only kind of natural from the Sullivan dictionary point of view, but also very useful. Okay, which I think also is kind of something new to the smooth dynamics community. I mean, it's like our contribution from complex dynamics. Okay, and so what about the first question we want to ask, the quasisymmetric uniformization problem? So, well, we want to study when the space is equipped with a visual metric is geometrically equivalent to some given standard space. Okay, in the classical uniformization problem in complex analysis, we're all very familiar, Riemann mapping theorem, etc. But in the context of quasi-symmetric uniformization problem, we want to ask a given metric space is homeomorphic to a standard metric space X0 D0 under what kind of condition the homeomorphism can be upgraded to a quasi-symmetry. Okay, so this is a recall of definition of quasi-symmetry. I think people here are familiar, but I just mentioned that, well, it's a homeomorphism that maps spheres to ellipse of controlled eccentricity. Okay, and there's a long history of quasi-symmetric uniformization. But let me just mention a few results. For example, Tukey and Vasilov studied the problem for S1, and Bonk and Kleiner studied, which was also mentioned in the conference, that an alpha two regular metric space a metric two-sphere is quasisymmetric equivalent to a standard two-sphere if and only if it's linearly locally contractible. But it's worth noting that for dimensions 3 and above, such theory, such results are not available. Okay, and in dimension 2, Cannon's conjecture on the other side of Salerno dictionary predicts that the visual sphere of a Gromov hyperbolic group whose boundary is homeomorphic to S2 is quasi-symmetrically equivalent to the Riemann sphere. Okay, and inspired by Cannon's conjecture, the work of Bunke and Mayer produced a key result, as stated here, that for expanding Thurston map on the two sphere, the visual sphere is quasi-symmetric equivalent to the standard sphere if and only if F is topological conjugate to our rational map. Okay, and a similar result was also obtained by Heisenberg and Pilgrim. It's a long story, but what about the motivation for our work? What about higher dimension of counterpart of Bunke-Mayer theorem? Well, we defined the counterpart of Thurston map, our combinatorial Thurston map. What about the counterpart to rational maps? Well, it was already mentioned in many previous works. It's related to uniformly quasi-regular. They are uniform quasi-regular maps. So first, let's recall quasi-regular maps. I think Pekka gave a great talk on such maps, and I just mentioned that it is, well, just recall quickly that it's a continuous map between oriented Riemannian manifolds, and it's K-quasi-regular if the map itself is in some Sobolev place, and then the distortion, there's some distortion control. And similarly, like the spheres are mapped to ellipse in a controlled way by the distortion K. Okay, and then there is a long history of study of quasi-regular maps as up to today, and Pekka gives such a great talk and works on such, and we by now know there is a property of quasi-regular maps include analogs of Liouville theorem, Montel theorem, Picard theorem, all the goodies in complex analysis. Okay, and what about dynamics, right? So the quasi-regular maps is done, it's just one map, and then we want to iterate it, and then we still get some control in a similar way as the kind of control we get from complex dynamics. So a quasi-regular map is uniformly quasi-regular if all its iteration have controlled distortion by the same control, by the same K. Okay, so that's the notion of uniform quasi-regular maps, and by the works of Ivanik, Martin, Mayer, etc., we know that uniform quasi-regular maps can be viewed as high dimensional counterpart of dynamics of rational maps on the Riemann sphere. Okay, so now let's recall the main theorem of Bunke and Mayer for quasi-symmetric uniformization for two sphere, and then we prove a higher dimensional analog for n bigger or equal to 3, expanding combinatorial Thurston map and its corresponding visual metric is quasi-symmetric. The corresponding visual metric is quasi-symmetric equivalent to the Riemannian metric if and only if the map is uniformly quasi-regular. So that's the first main theorem. Okay, and now the second main theorem is rigidity. So still in the same setting, for n bigger or equal to 3, and let F be an expanding combinatorial Thurston map of oriented closed connected Riemannian manifold of dimension n. Then F is uniform quasi-regular if and only if it is a quasi-regular lattice map, which I'll define, recall later soon. Okay, and the lattice map is in particular a special class of uniform quasi-regular maps, semi-conjugate to conformal linear maps. Okay, so what exactly do I mean? Lattice map? Well, uniform quasi-regular map is a lattice map if the following condition satisfied. There exists a discrete subgroup of the excuse me, isometric group of Rn, and one quasi-regular map phi, so-called strongly automorphic to the group. And so in particular, precisely means that any two points have the same image on the phi if and only if the 2 points are linked by one group element gamma. Okay, and a conformal phi map is just a translation and multiplication lambda and a rotation u. Okay, so it's a conformal, that's what we call conformal affine map. Okay, for which the diagram commutes. Here we have F, and on the top we have the given conformal affine map. Okay, so well, for rigidity of uniform quasi-regular maps, there's actually conjectures. For example, the conjecture of Martin and Mayer says that the map is uniform quasi-regular map whose Julia set. I forgot to mention that for uniform quasi-regular map, then it's so much like complex dynamics, and they admit the theory of Julia set and Fatou set, etc. So we can talk about corresponding Julia set and Fatou set. Okay, so the conjecture of Martin Mayer says that if the Julia set has positive measure, then the uniform quasi-regular map has to be lattice map. Okay, and then there is a variant of Martin Mayer conjecture, a question of Kangas-Niemi, I think also inspired by Pekka and Kangas-Niemi is former student of Pekka, as we know, and whether all non-constant and non-injective uniform quasi-regular maps on oriented close connected Riemannian manifold, the manifold is the manifold is not a rational homology sphere. All these kind of uniform quasi-regular maps, just lattice maps. Okay, so these are kind of questions people already ask about rigidity of uniform quasi-regular maps, and in a sense, we investigate such questions in the setting of combinatorially post-critical finite maps. Okay, and Martin and Mayer already know a lot about their conjecture. In particular, they prove that if the map is assuming we have a uniform quasi-regular map, if the set of so-called conical points of the map has positive measure, then the map is a lattice map. Okay, and the definition of a conical point is a bit complicated. I think we should probably just skip it. All right, and then so how do we prove our results? How do we prove our results? Well, we need to introduce some metric version of our uniform combinatorially post-critical finite uniform quasi-regular maps. So what we call uniform expanding BQS maps. Okay, so we'll define it in the next slide. But if we for orientation preserving branch cover maps, then our notion of uniform expanding BQS map, BQS stands for branched quasi-symmetry, if and only if the map is a chaotic lattice map. And a chaotic lattice map just means that, well, the subgroup is discrete and co-compact, and then the affine map has expansion, has lambda bigger than 1. Okay, and for this theorem, the dimension bigger than or equal to 3 is crucial. All right, so what is a branched quasisymmetry, or BQS, before uniform expanding? Let's just recall the notion of branch quasisymmetry. So branch quasisymmetry map is just a branched version of quasisymmetric map. Okay, so a map F between metric spaces satisfy this distortion condition for any pair of intersecting continuum. Okay, very similar to quasisymmetry, but we don't require homeomorphism. Then we call the map, if such inequality holds for all pairs of intersecting continuum, then we call the map branch quasisymmetry, abbreviated as BQS. All right, and Peking and my academic brother linguist already studied it. So in our setting, the map F is quasi-regular if and only if F is discrete, open, orientation preserving, and branch quasisymmetry. Okay, so that's why we say branch quasisymmetry is a metric version of quasi-regularity. All right, now we need to do dynamics. We need to iterate. So we need to define, introduce the notion of uniform expanding branch quasisymmetry, not uniformly. It makes a difference. So we call F is a uniform expanding branch quasisymmetry if there exists a finite cover by connected open subsets of the space and a homeomorphism such that the finite cover gives you, as you pull back the finite cover, the mesh goes to 0. That's the word expanding, what the word expanding means. And uniformly expanding branch quasisymmetry also requires that for all iteration, for all open set in the pullback of the open cover, the map restricted to the open set is uniformly eta branch quasisymmetry, of eta branch quasisymmetry for the uniform given eta. Okay, so this is our notion of uniform expanding branch quasisymmetry. And as you see, you have a branch cover, you pull it back, and it becomes finer and finer. That's the expanding part. And then on each open set map forward, you have eta branch quasisymmetry, no matter where you start to map. Okay, all right. So then, summarizing all the results we have discussed, we have the following equivalence. In the setting of expanding combinatorial Thurston map on oriented closed connected Riemannian manifold of dimension bigger than or equal to 3, and we consider the rho the visual metric, then the visual metric is quasi-symmetrically equivalent to the Riemannian metric if and only if the map is a uniform expanding BQS map, if and only if the map is a lattice map, if and only if the map is a uniform quasi-regular map. Okay, so what about the proofs? Okay, so the condition 1 and 2, well, 1 says the uniformization, and then 2 is a metric version of UQR map. So, well, 1 implies 2 because with respect to the visual metric, it's very easy to see from the definition that the map is uniformly expanding BQS. And then that property is preserved under quasisymmetry. So fairly simple. And 2 imply 1, you get quasisymmetry is established by metric properties of the cell decomposition. Because in the definition of uniform expanding, from the definition of combinatorial Thurston map, we have the cell decomposition and imposing the metric conditions. We have some quantitative control of the cellular sequence, and in particular, we can get. The control is summarized in this lemma. It's a bit too technical to discuss here, but let me just say that conceptually, it also is similar to another idea of Bank and Myers called quasi-visual approximation. So if you have a sequence of branch covers, sequence of open covers pulling back, and you can get quasi-symmetry out of it if you verify certain conditions called quasi-visual approximation. And here, basically, we use similar idea, but direct proof. All right. Now, what about 2 implies 3? What is 2? 2 is two is the uniform expanding BQS map, and 3 is the rigidity, the lattice map. Okay. So actually, in a related work of Heisenberg and Pilgrim on coarse expanding conformal systems, so-called CXC systems, similar rigidity was also proved. So we can also include their condition, Heisenberg-Pilgrim condition of CXC. So 2 implies 3 is actually the difficult part. So 2 implies 3 is the difficult part. So it requires we prove using uniform expanding BQS map to prove that every point is conical. I mean, the definition of conical point is complicated, and so as you can imagine, this part is a bit technical, but you can do that. You can prove from uniform expanding BQS map that every point is conical, and you can also quite straightforwardly prove that under the condition 2, the map is quasi-regular, uniform quasi-regular, combined with uniform quasi-regularity. And every point is conical. We can use the previously mentioned Martin-Mayer theorem to prove that the map is lattice. Okay, so over there they just require the set of conical points is of positive measure. Here we have every point is conical. Okay, and then 3 imply 2. Well, 3 imply CXC 2 prime. That's the content of the work of Heisenberg and Pilgrim. We can squeeze the notion of CXC in our list of equivalence. And then 2 prime imply 2. Well, you just estimate them with the metric properties. So I will skip that. Okay, and not terribly complicated. All right. Lastly, 3 imply 4. So 3 is the lattice map, and 4 is uniform quasi-regular. Well, once you know lattice map, the map is very special. Even though I think the properties of lattice map and what they really like, I think it's still quite mysterious in higher dimensions. Okay, not much. I mean, there are works, but I think many more works should be done on higher dimensional lattice maps. But at least from the definition, we can verify directly that lattice maps are uniform quasi-regular. That can be done. All right, and then lastly, we also have to come back to conical points. To prove uniform quasi-regular maps are lattice maps, then we need to use the combinatorial structure and the property of uniform quasi-regularity to prove that every point are conical. It's a separate proof. Previously, we also, on the different condition, we have to prove every point is conical. Here, under this set of conditions, we use a separate proof to prove every point is conical. Once that is proven, then being uniform quasi-regular, you already have, that's already given. So combine the uniform quasi-regularity and every point is conical. You can use again Martin and Mayer to deduce that the map is lattice. Okay. Yes. Exactly. Two and 4 imply 3. All right. Okay, thank you. Because Ilya have to leave early, so that's all for my talk. Thank you.